Good evening, everyone. Welcome to the second session on quantum optimization as a part of the Qiskit Fall Fest IIT Jodhpur 2025. Today we have with us Dr. Paweł Gora. Dr. Paweł Gora is the chairperson of the board of the Q World. Q World is an international non-profit organization dedicated to supporting education and research in quantum computing. He is also the founder and CEO of the Quantum AI Foundation, which focuses on advancing knowledge and collaborations in artificial intelligence and quantum technologies. Dr. Gora holds multiple degrees, including a PhD in computer science from the University of Warsaw, and has significant experience working in top tech organizations. His work spans AI applications in medicine, quantum technologies, and he actively leads community building efforts in quantum science through various education and outreach programs. With this short introduction, the floor is all yours, Dr. Gora, and you can start.
All right, thank you. Thank you for inviting me to give this talk, and thanks for the great introduction. Uh, yeah, so I believe that my affiliations at Qword Quantum AI Foundation have been already introduced. I'm also the coordinator of Q Poland, which is one of the Q cousins of Qword, and indeed, the goal of all this organization is uh, to support the education and research in new technologies, especially quantum computing. And in case of Qword, it's also building the global or contributing to the development of the global open ecosystem for quantum technologies. And today I will tell you about the quantum optimization. So I assume that you already know the basics of quantum computing and programming. So I will not explain everything from scratch. I assume that you know what's the qubit, what are the quantum gates, what are the quantum circuits, and so on. Perhaps you also know what are the possible applications of quantum computing, like breaking some classical cryptography algorithms, solving combinatorial optimization problems that frequently occur in different domains like finance, transport, logistics, AI as well. Almost the whole machine learning domain is about solving some optimization problems. When we train some neural networks, we basically minimize or try to find the weights of connections between neurons that minimize the loss function that is defined by us. We can also use quantum computers to sample from distributions that are difficult for classical computers, like the Boltzmann distribution is an example. It also has applications in machine learning. We can also have quantum random number generators. We can simulate quantum processes, which may find applications to discover new materials, new drugs. We can try to apply quantum computers to generate art, like music, or search in unstructured databases using Grover search algorithm. But today I will focus on solving optimization problems and why we can even consider quantum computers for this, and what actually these combinatorial optimization problems are. So in combinatorial optimization problems, we search for the best of many possible combinations. So these problems include some scheduling challenges, like should I ship this package on this track or the next one? Or what's the most efficient route a traveling salesperson should take to visit different cities? So this is the famous traveling salesman problem, which is proven to be NP hard. So it's believed to be difficult for classical computers in general, but in practice, it turns out that it's actually not that easy to find the instances of the traveling salesman problem that are really difficult for classical computers as well. But there are also some variants, some more general variants of these routing problems, and later in this talk I will also tell about them. Okay, so we know what are these combinatorial optimization problems, and it turns out that physics can help solve these sorts of problems because we can frame them as energy minimization problems. And a fundamental rule of physics is that everything tends to seek a minimum energy states. Like objects slide down hills, how things cool down over time in closed environments, of course. And this behavior is also true in the world of quantum physics. And for example, during this talk, I will tell you about something that's called quantum annealing that simply uses quantum physics to find low energy states of a problem and therefore the optimal or near optimal combination of elements. But before I go to quantum annealing, I also wanted to introduce some other techniques that are more related to quantum circuits and quantum gates, which have been probably covered during the earlier lectures, I believe. And for this kind of problems, a class of quantum algorithms that is quite suitable is called variation quantum algorithms. So these algorithms share a common structure where a task is encoded into a parameterized cost function that is called ansatz, that is evaluated using a quantum computer. And there's also a classical optimizer that trains the parameters in the variation quantum algorithm. So actually, this is not fully quantum algorithm. It is a hybrid algorithm, and the actual optimization procedure is performed using a classical solver. So it's not really the quantum optimization. But it's good to know that these algorithms have emerged as the leading strategy to obtain some kind of quantum advantage on the so-called NISQ or noisy intermediate scale quantum devices. And here you can also see a visualization of the structure of the variation quantum algorithms. So why these algorithms are good for NISQ devices and NISQ area in which we are living now? So what are the main advantages of the NISQ devices? So there's a lot of noise. So every time we apply a quantum gate, there is some substantial chance, like 0.1%, that will actually apply a different gate. And this is just one of many flavors of noise we can get. The qubits don't live for too long. So after some time, we can be pretty confident that whatever information was stored in our system, it is lost. So the number of operations we can perform in this time is limited. We don't have too many qubits, and there might be some restrictions on which qubits can interact with each other. So for which qubits we can apply the CNOT gate, for example. So as a consequence, there is a set of restrictions on our quantum circuit, like we can use small number of operations per qubit. So this is called the circuit depth, so the number of operations per qubit that we can apply. And we cannot assume that everything will go according to the plan and there will be no errors along the way. But even if there are some errors, we should still get a reasonable answer, though it will not be perfect usually. We call this robustness. And obviously, we cannot use more qubits than we have. All right, so why these variation quantum algorithms are good for the NISQ area? So they are pretty flexible when it comes to the circuit depth. So we can use a pretty simple ansatz. So just to recall, this ansatz is this parameterized variation quantum circuit. If you want to keep our circuit very shallow, but once we have a machine which allows for a deeper circuit, uh, we can use more sophisticated ansatz and the performance might increase as a result. And VQA have been shown to be somehow resistant to noise. So even in the presence of noise, up to some levels, of course, it gives the correct results. Some people even claim that a pinch of noise might help with the optimization process because it helps to escape local minima. But it's still actually an open question whether the quantum noise can really give an advantage here, because even the quantum noise can be somehow and to some level of up to some level, of course, simulated using quantum computers. But we already have some demonstrations of problems or and quantum circuits for which um, the quantum computers already give an advantage. So it's not that easy to simulate in the given quantum computations, which means that perhaps this quantum noise can really give some advantage. But as usually in this kind of problems, it's very difficult to really prove that there is the actual quantum advantage in this application, of course. And finally, some examples of this variation quantum algorithms. So there are basically two main classes: quantum approximate optimization algorithms, or QAOA in short. And there are also some variants like recursive QAOA or warm start QAOA, in which we start from an initial solution that we just try to improve. And there could be a variation quantum eigensolver and its variants like filter VQE, layered VQE, or combination of both approaches. All right, but as I told you, these variation quantum algorithms can be used to solve some optimization problems, but these are other hybrid algorithms, and this quantum part is not exactly responsible for the optimization part. The actual optimization part is rather performed using classical solvers. So instead, in this talk, I will rather focus on another class of algorithms that are called quantum annealing, or that's called quantum annealing. And this is quite interesting because there is only one company developing this kind of approaches. This company is called D-Wave. It's headquartered in Canada, and they already published some uh, articles demonstrating that they managed to use their quantum annealer machines to solve some optimization problems. So here you can see just the titles of some articles on the internet from 2017, so it's already 8 years ago. Like Volkswagen uses quantum computing to fight Beijing traffic, and Volkswagen teamed with D-Wave Systems to run a traffic flow algorithm on a quantum computer with encouraging results, and Volkswagen and Google to bring quantum computing benefits to cars. So these are just examples. So now I will tell you about the specific use case that the researchers from D-Wave tackled together with researchers from Volkswagen. And based on this use case, I will try to later explain or give you intuition how exactly this quantum annealing works. But first, a bit of theory. The quantum annealing is related to something that's also called the adiabatic quantum computing. So what is the adiabatic quantum computing? So in adiabatic process, an adiabatic process is a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. And in such adiabatic processes, energy is transferred to the surroundings only as work. So there is an idea, there was an idea to build something like an adiabatic quantum computer, in which the idea for quantum computations is as follows. So first, we prepare a potentially complicated Hamiltonian, whose ground state describes the solution to the problem of interest. I'm not sure if you have covered the Hamiltonians in some of the previous talks, but just in case, you can think for a purpose of this lecture, you can think about a Hamiltonian as a function that takes a given quantum state and returns the energy of a system in this state. So we need to find um, a Hamiltonian whose ground state describes the solution to the problem of interest. The ground state, which means that the state with the minimum energy. And then a system with a simple Hamiltonian is prepared. So, for example, this could be just a superposition of all possible states. And this superposition, like after application of the Hadamard's matrix, could be the ground state, for example. And finally, the simple Hamiltonian is adiabatically evolved to the desired complicated Hamiltonian. So there should be this adiabatic evolution, which means that there cannot be any transfer of heat or matter into or out of this system. And but the adiabatic theorem, so if we ensure that there is no transfer of heat or matter, the system remains in the ground state, so in the state of the global minimum. So at the end, the state of the system describes the solution to the problem. So this quotation is taken from Wikipedia, of course, but it's I think it's quite good, and it explains the nature of adiabatic quantum computations, right? So we have to define two Hamiltonians or two functions. The one function should be easy to prepare for our quantum computer. So as I said, this could be just a superposition of all possible states, and or a function for which the superposition of all possible states is the ground state, so it's the minimum energy state. And then there should be a complicated Hamiltonian corresponding to our optimization problems, for which the ground state of the Hamiltonian should correspond to the global minimum of our optimization problem. So this part is usually more difficult. And also the whole adiabatic evolution is difficult. So the first thing is that it's difficult to ensure in practice, in real world, that we have a really adiabatic process. So this is one thing. And another thing is that in order to ensure that our system stays in the ground state, this evolution should be performed slow enough. And there are even some mathematical formulas telling us how slow the evolution should be. And it turns out that in practice, the pace of evolution can be so slow, or should has to be so slow that um, we cannot guarantee that this algorithm will be better than classical algorithms, right? So perhaps there will be no advantage. But there's also an interesting theoretical result that proving that there's a proof that this adiabatic quantum computing model is polynomial equivalent to conventional quantum computing in the circuit model. So using standard quantum gates. Yeah. So this is a theoretical result, but um, in practice, it's more difficult to achieve, of course. And this is just a formula visualizing the whole idea. So we have two Hamiltonians. So one that is here mentioned as Hi, and this should be Hamiltonian for which the ground state is easy to prepare. And then there is the Hamiltonian corresponding to the so-called Ising model, and I will soon explain what the Ising model is. And this Hamiltonian should correspond to our optimization problem, so that the global minimum of this function should correspond to the global minimum of our optimization problem, or at least to a reasonably good solution of our optimization problem. Yes, and how to perform this, let's say, adiabatic evolution in practice. So in practice, it can be done by, so in general, our optimization problem should be encoded in a ferromagnetic, for example, or another magnetic system. So that's why we introduced the Ising model, and I will soon tell what exactly is this Ising model. And in this system, we have to change the strength of the magnetic field to slowly go from the initial Hamiltonian to the desired Hamiltonian corresponding to our optimization problem. And by the adiabatic theorem, if we change the strength of the magnetic field slow enough, then the final state will be the solution of our problem, so the global optimum. Uh, and But in practice, it's difficult. It's difficult to ensure that we have the adiabatic process. It's difficult to ensure that the evolution is slow enough, because in some cases it should be really, really slow. So instead, we can do it faster, and then we cannot guarantee that our system will stay in the global optimum. But there is still a chance that it will, let's say, jump from our global minimum, but that the solution that we find at the end can be still a relatively good solution to our optimization problem. And this solution could be just found faster. And this is the idea of the quantum annealing. And we can consider it as a heuristic, actually, right? Because in this case, we cannot guarantee that we'll stay in the global optimum of our optimization problem and our system, our quantum system. But um, there is a hope that the solution that we find is can be still um, satisfactory, can be still sufficient for us, good enough. So that's the idea. And now about the Ising model. So the Ising model is a model of ferromagnetism. It's traditionally used in statistical mechanics. So we have some binary variables corresponding to spin up and spin down, and these states correspond to +1 and -1 values. So not exactly 1 and 0 as in standard, let's say, binary optimization problems. And these values +1 and -1 may correspond to atomic spins or magnetic dipole moments. And we have some relationships between the spins represented by couplings that are correlations or anti-correlations. And then the objective energy function, the Hamiltonian, expressed as an Ising model, is as follows, right? So here you can see that we have some coefficients corresponding to qubit biases, Hi, and we have some quadratic coefficients corresponding to coupling strengths between qubits and between these, let's say, variables Si, Sj. So this is a polynomial of degree at most 2 of multiple binary variables, but these variables correspond to +1 and -1 if we want to get the energy of our quantum system at the end. But in mathematics and computer science, we have something similar that is called QUBO, which is the abbreviation of quadratic unconstrained binary optimization. So these problems are traditionally used in computer science. So actually, I've just found that there is a mistake in the title of this slide. It should be quadratic unconstrained binary optimization, as it is in the next line. And here the variables are true and false, so they correspond to values 1 and 0. And then the QUBO is can be defined using an upper diagonal matrix Q, which is an n times n upper triangular matrix of real weights. So there are real coefficients. And x is a vector of binary variables. Um, and the goal is to minimize this function, right? So here we have just coefficients, and we have binary variables xi, xj. And as you can see, this formula is very similar to the function of the energy of the Hamiltonian. In case of the Ising model, the main difference is that instead of 1, 0, we have values +1 and -1 to get the energy. But there is the isomorphism between these two structures, these two functions, actually, right? So it turns out that if we are able to define our optimization problem in terms of QUBO, so if we define our optimization problem as a problem of minimizing a function that is defined in this way, then we can encode it in a ferromagnetic so that the energy of our quantum system is expressed using a similar formula, similar to our optimization problem. And the ground state, the minimum energy state, will correspond to the global minimum of our optimization problem, right? So this could be our final desired Hamiltonian, as you can see. So this is the corresponding Hamiltonian corresponding of the corresponding Ising model that could correspond to our combinatorial optimization problem. Yes, and we can evolve our quantum system starting from a simple Hamiltonian to the desired Hamiltonian by changing the strength of the magnetic field slowly. So that's the idea. So now the main problem is how to define our optimization problems in this way, right? Because the rest is actually physics, right? Then we encode our problem uh, in a quantum annealer and perform computations, and then we can get a solution. And in theory, this should be the global optimum. In practice, I've already explained why it's difficult to ensure. So in practice, it doesn't work as the theory predicts, but there is still hope, and in some cases, we can achieve some good results. And there is a hope that we can achieve good results. So this could be a sufficiently good heuristic method. Um, in this quantum annealing process, there is a one quantum phenomenon that plays a crucial role that is called the quantum tunneling. So when we look at um, the landscape of our function that we want to optimize, I said that we start from a simple Hamiltonian. So initially, then this landscape can be relatively simple, but then when we change the strength of the magnetic field, we change the landscape, right? So when the system was in the global optimum, then when we evolve our function according to this formula and we go toward the final Hamiltonian, we modify this landscape of the function, and the point that was, let's say, the global optimum of one function, uh, may become just a standard point far from global optimum for another function, but there could be a thermal jump performed thanks to this process of quantum tunneling, and the system may again uh, just evolve towards another global or local optimum, right? Depending on how we just change the strength of the magnetic field. So this is a reason why uh, we can hope that the final solution that is returned by our quantum annealing solver is reasonably good. Uh, and this is something that it's difficult to achieve in case of classical algorithms. So how this can be applied in practice? So I will explain this use case published by the researcher from Volkswagen and D-Wave as I believe it's quite easy to understand, relatively easy to understand and explain. So the title of the paper is Traffic Flow Optimization Using a Quantum Annealer. I think it's still publicly available on the internet, so you can try to find it on the internet. And what was the idea? The researchers built a realistic road network, and they had routes from the real traffic navigation data, real GPS data. So there was a data set of routes that was called T-Drive. As far as I remember, it was prepared by scientists from Microsoft Research, and it was publicly available. So this was a data set of the routes of taxis in Beijing, um, and they took the routes from the Beijing city center um, to the airport. And for each taxi, they added two possible routes between the source and the destination. And of course, it was assumed that the cars may share road segments. There was also an assumption that the travel time is proportional to the square of the number of cars on a route, which is a simplification, but it's a reasonable simplification. Because when you think about it, um, the travel time is usually, well, close to inversely proportional to the number of cars on a given route, at least in some regimes of the traffic density. So mm, when we multiply the time by the number of cars, then it's like it's like a square function. Um, so it's a simplification, but it's not that far from the true. And now we want to minimize the total travel time. So how we can do it? So we introduce binary variables qij, and these binary variables indicate whether car I takes route j. So if the value is 1, it means that the car I took the route j, and the value 0 means that this car doesn't take the route j. So of course every car has to take exactly one route, one out of three. Yeah, so just to recall, we had original routes from the real world, and there were two additional routes added by the researchers. So for every car, there were three options, three alternatives. Yes, for J1 to 3. So, but this condition should be satisfied, right? Exactly one of these variables should be equal to 1. So this condition should be satisfied. And then we introduce the set of these binary variables that are associated with routes that share a street segment S. And then what's the total cost of traveling? So what's the total time of traveling through this road segment S for all the vehicles that travel through this road segment? So it was assumed that this time is proportional to the square of a number of cars on a route. So when we make this this sum of all variables that um, are related to are associated with the road segment S, then we know that the value 1 is only for the cars that really selected a given route. So they also take the road segment S. So this sum is just the total number of cars that selected or just go through the street segment S. So the total time of travel for all the cars is just the square, according to our assumption. As I've told you, it is a simplification, but it's a reasonable simplification. So then the total cost of travel on all road segments in our road network is just the sum over all road segments, right? So this is something that we want to minimize. But we can easily see that the minimum of this function is 0 when all the variables are equal to 0. Yes? But this solution is not interesting for us because it means that uh, the cars actually do not travel. They do not select any route because this condition is not satisfied, right? So we want every car to select at least one route. So we want to minimize the cost, but at the same time, we have to ensure that this condition is satisfied, that every car selects exactly one route. So what to do in order to ensure that um, this condition is satisfied for every car? So let's define this formula, this function, that for all the variables qij computes this part, and we just calculate the sum over all vehicles. So we know that if this condition is satisfied for all the vehicles, then this sum should be equal to 0, right? And otherwise, if this condition is not satisfied for at least one car, then this sum is greater than 0. So now we can add a quite large coefficient. It can be really, really large in order to ensure that if this sum is not equal to 0, then the value of the whole sum is very large, like much larger than even the maximum or the average value of the cost function at least, right? It should be more or less the same order of magnitude, but this should be more than the typical values of the cost function. So that when we apply any solver, whether it's a quantum annealer or some classical solvers, the solvers shouldn't consider the solutions that do not satisfy the constraint as good solution for our optimization problem, because this sum can be small, but if this condition is not satisfied, then this part will be very large. So the whole sum, the whole objective function will be very large as well. So the solvers like quantum annealer will try to look for the solutions for which this part is equal to 0. And under this constraint satisfied, they will look for the solutions for which this cost function is small as well. So that's the whole idea, and the similar procedure is applied in um, all the cases related to quantum annealing. So we have to define our cost function that we want to minimize and then define formulas corresponding to satisfying different constraints that we have. Sometimes we may try to relax some constraints, right? And try to find a trade-off between satisfying the constraints and minimizing the cost function. So there are also some such ideas. All right, let's go further. So we can see when we analyze this objective function, so we know that the cost function is the polynomial of multiple binary degrees uh, of degree at of multiple binary variables of degree at most 2. So this is cubo, and this part is cubo as well. It's also a polynomial of multiple binary variables of degree at most 2, right? So this is a properly defined cubo formulation. It corresponds to some Ising model, so we can encode it in a quantum annealer and perform computations, right? And this is exactly what the researchers from D-Wave and Volkswagen did in 2017 already. They performed computations, and that was the result, right? So they had 418 cars in their dataset with 3 times more logical variables, because for every vehicle they had 3 variables, 3 options. So in total, it gives 3 to the power of 418 possible solutions. So it's a very, very large space of options. We cannot classically we cannot explore all these options. So we need some smarter algorithms. So as a result, there was a relatively small number of streets that were heavily occupied. So this is the so on the left on the left figure you can see how exactly the traffic looked, or how the taxis were distributed in the real world in Beijing, and the more red color means that uh, there are more cars basically. And this is the distribution of the route assignments and the densities of cars for the solution that was found by the quantum annealer. And the computations took only 22 seconds. And of course, someone may ask, is it possible, or do we have a quantum advantage? Is it possible to do something similar using classical algorithms? Yes. So of course, there was no proof that there is no classical algorithm that cannot do it. So when you check the paper that was published by researchers from D-Wave and Volkswagen, you will see only information about the quantum methods, but not about any classical algorithms. So it's hard to say, but I'm pretty sure that some classical solvers like heuristics, meta heuristics like simulated annealing genetic algorithms, particle swarm optimization, and so on, or memetic algorithms could be able to find similarly good solutions. So it doesn't prove that we already have quantum advantage in this case. But it already demonstrates that these quantum annealing machines useful, can be useful, can be applied to solve some real-world challenges. Maybe not better than classical computers, but they are already useful. Okay, and now I will demonstrate another example, but maybe before I move forward, perhaps there are some questions to the first part, to the theory or the results that were presented by D-Wave and Volkswagen, because I think that now the next slides can be maybe a bit more difficult. So, okay, I do not hear any questions, so let's move forward. Um, so now I will tell you about another optimization problem that can be tackled using quantum algorithms, in particular quantum annealing. This is the so-called the vehicle routing problem and its variants like capacited vehicle routing problem or vehicle routing problem with time windows. So as an input, we have a directed graph with non-negative costs assigned to edges. So this could be also travel times as in the previous use case. And probably you've heard about the traveling salesman problem. It is a problem in which we have n selected vertices in the graph. So these are our customers. And then we ask the following question. What is the shortest possible route that visits all of them and returns to the original vertex, to our depot? Okay? And then we have a vehicle routing problem in which that is similar, but in this case, we also have n selected vertices in the graph. So we can think about them as our customers if we are an e-commerce platform or logistic company that has to deliver something to our customers. But then the question is more general. What is the optimal set of up to m routes which in total visit all the selected vertices and start and end in the depot? So in the traveling salesman problem, this m is equal to 1. And here we might have several routes. We may have several vehicles. We can just follow one route, then go back to the depot and uh, take some other products that should be delivered to other customers and so on. So this is the difference. And there are also some variants like CVRP, capacity vehicle routing problem, which is just the vehicle routing problem with bounded capacities of vehicles. We may also add time windows. So, and then we have the CVRP TW, which is the vehicle routing problem with time windows constraints. What is important is that all these problems are NP hard because we can proof for the traveling salesman problem that it is NP-hard, and the other problems are just generalizations of the traveling salesman problem. So yeah, if we are able to solve any of them in polynomial time, then the traveling salesman problem will be also solved in polynomial time. But we believe that it's not possible. It has been proven that the TSP is NP-hard, so we do not expect fast classical algorithms able to solve all the possible instances of the TSP in polynomial time. But as I said, in practice, when we have in real-world networks, we usually have Euclidean graphs that are planar or close to planar. So there are just some very special graphs, and for this kind of problems, it turns out that for this kind of problems, the classical heuristics are also quite good already. Okay, but let's go to the vehicle routing problem and solving it using the quantum annealing. So we have to introduce the following notation. So we have the set of identifiers of trucks or vehicles. We also have a set of identifiers of the nodes, where n plus 1 can be denoted as our depot, where we should start and end. And we have n customers in this case. We also have the cost of travel from node I to node J. Um, this notation is Cij, and of course, cost of staying in a given place, in a given location, is 0. Then we introduce the following binary variables: x, I, j, k, and these variables should be equal to 1 if in a given setting the vehicle I visits the node j as the kth location on its route. Otherwise, it should be 0. So now a few observations. For each vehicle I, xi n plus 1, 0 is equal to 1, which means that the depot is always the initial 0th location, right? And this variable xij0 is equal to 0 for other j's, right? So when the vehicle I starts its drive, we are in the time 0, it has to be in the depot. And then if xi n plus 1 l is equal to 1 for some l that is greater than 0, then for all times after l, the xij w should be equal to 0 for j lower than n plus 1, but for j equal to n plus 1, it should be 1, which means that the depot is always the last location on each route, and each car stays in the depot after reaching it. So here we assume that instead of having just a single car that just starts at the depot, visits some customers, and travels back to the depot, and then takes another route, when the vehicle travels back to the depot, it just stays there. So there are some other cars that have to serve the other customers. So this is the idea here. And then how the Kubo formulation can be defined. So when you look at it, you can see that it's much more complicated than what was proposed in the previous use case by researchers from D-Wave and Volkswagen. So there are three components, and the first component of the sum is a sum of all costs of travels from the depot to the first visited node, right? So yes, here we have m vehicles. So here we have time number 1, and then uh, this is a binary variable indicating that the vehicle is in point in the location n, and then we have the cost of traveling from the depot to this location n, right? So this is just the cost of travel uh, to the depot, from the depot to the first visited node. The second component is the cost of the last section of a route to the depot, in a special case when a single car serves all n orders, and only in such a case the component can be greater than 0. Okay, and the last part is the cost of all other sections of routes. All right, so now let's consider a binary function that takes n binary variables and returns the sum of these variables um, reduced by 1, and then we calculate the square. So we can observe that the minimum value of this function is equal to 0, and this value can be achieved only if exactly one of these binary variables is equal to 1. Okay, then we have the minimum. So how we can use it? So now, to assure that each vehicle is served by exactly one vehicle and that exactly once, and that each vehicle is in exactly one place at a given time, we have to add the following term to the cubo formulation. So this is this. Let's analyze this. The first component. Here we have the sum over different locations. So k is the location. The first in this index corresponds to our vehicles. So we have different vehicles, right? And we have different times as well. So this means that the location k. So when if the location k is visited by only one vehicle and only once, then this component is equal to 0, and only then. So if a given location is visited more than once, then this component is not equal to 0, according to our definition. So if we want to minimize this component, or by minimizing this component, we ensure that each delivery or each location is served by exactly one vehicle and exactly once. And for the second component, here we have m and n, so we have a given vehicle at a given time, and there are n plus 1 locations, including the depot. And then this is the minimum if and only if only one variable is equal to 1, which means that at a given time, a given vehicle has to be in exactly one place, right? And this is equal to 0 if and only if all these components for all m and n are equal to 0, and they are equal to 0 when the vehicle m at the time step n is in exactly one location. So then we can construct the final QBO, quadratic and constrained binary optimization problem formulation, that corresponds to our cost function that we want to minimize. So this is the function that I explained, and then the component corresponding to satisfying the constraints. And we have some parameters A1, A2 that should be properly set to ensure that the solution found by the quantum annealer minimizes the cost C and satisfies the constraints Q, right? So that's the idea. And then we can try to improve this formulation. So we can decrease the number of variables for each vehicle by assuming that every vehicle serves approximately the same number of orders, like up to A plus L deliveries, where A is the total number of orders divided by the number of vehicles, so N divided by M, according to our notation, and L is a parameter that controls the number of orders. So, this is a realistic assumption because in practice we usually want our fleet to be evenly loaded so that every vehicle serves more or less the same number of customers. So it's reasonable to assume that they have more or less the same number of deliveries, and thanks to that we can decrease the number of variables for each vehicle. And by decreasing the number of variables, we also decrease the number of qubits, so we make our optimization problem easier for our quantum annealing solver. Also, we can first classically cluster the nodes and solve TSP using a quantum annealer. So this is called the DB-scan solver because we can perform the clustering using the so-called recursive DB-scan algorithm, which is a classical clustering algorithm. We can also do something opposite. So we can first solve an instance of the traveling salesman problem. So this should be TSP, not TSF, using a quantum annealer, and then generate routes classically, for example, using dynamic programming, as this is the so-called solution partitioning solver, right? So here some details about the average partitioning solver. I think I've already explained it enough. We have this parameter that's called the limit radius. In case of the DB-scan solver, this is a hybrid algorithm. It uses a recursive DB-scan as a classical clustering algorithm with limited size of clusters. And then when we divide our road network graph and the set of customers into clusters, we can solve the instances of the traveling salesman problem for each of the clusters separately. Yes, and then the TSP can be solved using our quantum annealer. And then again, when you look at the Kubo formulation, when we have just a single vehicle, then we have the instance of the traveling an instance of the traveling salesman problem, and again it significantly reduces the number of variables, right? So this is a simplification. And then if the number of clusters is equal to the number of vehicles, the answer is known immediately. Otherwise, the solver runs recursively considering clusters as deliveries, so that each cluster contains orders, which in the final result are served one after another without leaving the cluster. And actually, by limiting the total sum of weights of deliveries in clusters, this algorithm can solve instances of this capacitated vehicle routing problem if all capacities of vehicles are equal, right? So we can solve not only the vehicle routing problem, but also capacitated vehicle routing problem. And another approach called SPS, or solution partitioning solver. So I already said that it works in the opposite way to the DB-scan solver. So it first uh, generates a solution for the traveling salesman problem for our road network graph. And we can do it using our quantum algorithm again. So as I've told you, when we solve an instance of the traveling salesman problem, then we reduce the number of vehicles that we have, so the problem is easier for the quantum solver. And then when we have the solution, we can try to divide it into consecutive intervals, which are the solution for the capacitated vehicle routing problem. So we divide the solution for TSP into clusters, and then we assume that each cluster is served by one vehicle. So how to do it? This can be done using a dynamic programming. So this is a classical algorithm, but maybe I'll just explain it briefly. So let D1, Dn be the TSP solution for n customers. Let PV be a capacity of the vehicle V. Let Wij be the sum of weights of orders Di plus 1, Dj, and so on, in the order corresponding to TSP solution, of course. And let cost ij be the total cost of serving only orders di to dj. Also let dpis be the cost of the best solution for orders from d1 to di and for the set of vehicles s. And now the dynamic programming formula for solving the capacitive vehicle routing problem is given by this form. So in order to calculate it, the cost of the best solution for the orders from 1 to I and for the set of vehicles S, we just look for a smaller set of vehicles and assume that a new vehicle solves uh, or travels from uh, or visits all the nodes from j plus 1 to I, so that here we take the cost up to the nodes j, and we take the minimum over all the vehicles, for example, right? And then if we assume that the capacities of vehicles are the same, then this problem is even easier. So in practice, this approach can give good solutions. So for example, we can also assume that instead of having as vehicles, we can consider a sequence of them by assuming that we attach them to deliveries in such an order as well. And then this dynamic programming formula can be simplified and computed efficiently by just a simple observation that we can just easily compute this minimum, right? So we can now select some random permutations of vehicles and perform dynamic programming for each of them, or just assume that the vehicles are indistinguishable, and then the problem becomes even easier. So now about some results. We perform some computations using the solvers that I just described, both quantum and hybrid, on a standard benchmark dataset for the capacitated vehicle routing problem, that is well known and frequently studied by the scientific community. And there are 14 tests with different number of vehicles, capacities, and number of orders. So these are just some examples. We have the names of the test, number of vehicles, the capacities, number of orders. Okay, but we also built another more realistic data set based on the realistic road network of Belgium, close to the Brussels. This was acquired from the OpenStreetMap service, which is an open source road network map of the world. And there were in total 51 instances, and we consider different number of orders from 1 to 200 and different locations of orders and depots. So these are just some example of test cases from these realistic road networks. And what are the results of experiments? So actually we perform computations on three, let's say, configurations of our hardware. Let's say there was just a standard quantum processing unit, QPU in short. There was a simulator of the quantum annealing, but on CPU. And there was a hybrid approach, so that some computations were performed on the quantum processing unit and some on the classical processing unit. So even for small it turns out that even for small instances, the quantum processing unit really struggled to find a good solution. So we had to use either the hybrid solver or the simulator of the quantum annealing. When we perform computations with the average partitioning solver, which already reduced the number of qubits, the number of variables and the required qubits, then the results were better, but still we struggled. Um, so eventually, we decided to just give up with the full qubit solver, as the number of qubits that was needed was just too large, even for one, two, or three vehicles. For the average partitioning solver, we achieved better results using both the simulation and the hybrid solver, but not the quantum solver yet. And for the DBSCAN solver, the results were maybe not that good on the simulator. But then when we run experiments on even larger instances, when there were large number of customers to be visited, it turned out that this approach, in which we first cluster all the vehicles and then solve or try to find solutions for the clusters, gave better results than the average partitioning solver. Of course, here we used the simulations of quantum annealing and not the full quantum annealing. Okay, so we observed that there could be an advantage of clustering all the uh, nodes in the graph first for large instances, and then performing computations or trying to find solutions for the traveling salesman problem, right? So that was the idea. And then when we compared the solution partitioning solver with this DBSCAN solver, it turned out that the approach in which we first solve an instance of the traveling salesman problem, but using a simulator of a quantum annealing, and then divide the solution into clusters, we can get even better results than for this DBSCAN solver. So then finally we compared this solution partitioning solver with some classical solvers like simulating annealing, B algorithm, evolutionary computations. So it turned out that for this, let's say, artificial or the instances, the real world instances from our from the dataset that we built from the road network in Belgium, and the results of the solution partitioning solver was usually worse than for the evolutionary computations, but it was comparable or sometimes better than the solutions for the other classical solvers. Um, yeah, so this was basically the setup of experiments, right? To compare the goal was to compare the results of different algorithms on several data sets. We ran experiments using the OSD platform and uh, two solvers, QBSolve on QPU and simulation of the QB solver, and there was a hybrid solver in which quantum processing unit and classical processing unit uh, were used at the same time. And these were the algorithms that we tested for the, as benchmarks: simulated annealing, B algorithm, evolutionary annealing, and DB-scan with simulated annealing. So these are fully classical algorithms, well established in the scientific literature. So here once again the summary of the data sets and the final conclusions from this experiment. So it doesn't make sense to run experiments on the quantum processing unit only for large test cases, unfortunately. So the number of variables is just too large. But the solution partitioning solver, especially with QBsolve run on the CPU, so the simulation of quantum annealing, can give the best result among, let's say, these quantum algorithms. And we compare this solution partitioning solver with some classical meta heuristics, and it usually gives a bit worse, but sometimes better results. And there is still an open repository with the code that we use for experiments, so you can try to use it if you are interested. And this is the final table with the final results, in which the solution partitioning solver was applied to solve the instances from the Christofides dataset this time. So it was not for the instances based on real-world data, but these were just the standard instances from the Christofides dataset. And you can see that the results were usually worse than in case of the DB scan solver with simulated annealing. Also, usually worse than for evolutionary annealing. But sometimes this DB scan solver with simulated annealing was not able to give good results. And in these cases, this solution partitioning solver was better than the other classical solvers that we tested. So this is an interesting result, in my opinion. Um, all right. Um, yeah. So this research was published in a paper, New Hybrid Quantum Annealing for Solving Vehicle Routing Problem. It was also supported by the EIT in the project, the Green Last Delivery. It was realized at the University of Warsaw with Colroyd Group from Belgium. So this is one of the reasons why we use data from the road network in Belgium, University of Cambridge, and Technion. What are the other research directions in this case? So of course we can try to use the VQE or QAOA algorithms and their variants, and I also introduced them at the beginning of this talk. There is a challenge with ensuring scalability of the algorithms. So that's why um, perhaps instead of running simulations of quantum annealing, we can also try to perform some kind of classical preprocessing of the inputs, like perform graph clustering as in the DB-scan solver, or graph coarsening. And I will tell more about the graph coarsening soon in the next slides. Of course, it's very interesting to investigate for which scenarios the hybrid algorithms give the best results comparing to classical algorithms. So, alternatively, for which scenarios we may expect some advantages in the future. This is a very interesting question, an important question. So, the solvers that I presented are able to solve an instances of the CVRP, so capacity vehicle routing problem, but without time windows yet. So how to extend them to time windows. So I can tell you that there are already some research works and research publications on solving the capacity vehicle routing problem with time windows using quantum annealing, but there are some other QUBO formulations, not the QUBO formulations that I presented here. So we can also investigate some other QUBO formulations. Finally, we can also try to apply some machine learning techniques to find good values of these relaxation parameters that stay in front of the QUBO part corresponding to satisfying the constraints. A few words about the graph coarsening. So the idea is that if some um, nodes in our graph are relatively close, so the idea is that perhaps they should be visited in a row. uh, so uh, then it doesn't make sense to visit one node, go to a node from totally different in totally different location, and then go back here. So the idea is that we can just coarsen the graph, and instead of having, let's say, two nodes CD, we can consider it as a single node, and the same for the nodes F and G, right? And then we can coarsen an initial graph, find a solution for much smaller graph uh, that our quantum or hybrids algorithms could tackle easily, because it also requires lower number of qubits and variables. And then we can try to find the solution and then rebuild the solution to for the original graph using some classical methods. So we can have to apply classical pre-processing and classical post-processing. And we perform these experiments, and it turned out that indeed, depending on the scale of the, let's say, coarsening, we can achieve better results on the Christofides dataset for the solution partitioning solver. Um, and the results were published in this research article about graph coarsening approach to the vehicle routing problem and approximation strategy. It was published in January this year, so you can check the details there. There's finally another interesting approach on applying machine learning techniques to find good values of this relaxation parameter that stays in front of the cubo part corresponding to satisfying the constraints. So I told you that sometimes we may want to relax our constraints, uh, and why we may want to do it. So the idea is that, when we set the value of this parameter staying in front of the cubo part corresponding to satisfying the constraints to very, very high values, then this component dominates the whole cubo, and the cubo part corresponding to minimizing our cost function is negligible. So the solver struggles to find good solutions for this cost function. So the idea is that maybe this parameter should have lower values, and sometimes with some probability, the solution found by the solver will not be a feasible solution, so it will not satisfy the constraints. But it should be easier for our quantum solver, for the quantum annealing, to find better values for our cost function. So if the probability of finding feasible solutions is still high enough, like 20%, 30%, then we can just repeat our computations multiple times. And then after like 5, 10 tries, we should be able to find feasible solution. But this feasible solution should be quite good this time, because it should be easier for the solver to find good values for our cost function that we want to minimize, because this component corresponding to satisfying the constraints doesn't dominate the whole objective function. Okay, so that's the idea. So the idea is to find good values of this relaxation parameter staying in front of the cubo part corresponding to satisfying the constraints. And actually, there is a trade-off, between the quality of the solutions and the probability of obtaining feasible solutions. So it's important to find good balance, and how we can do it. So the idea is that using a standard cubo solver for different instances of the graph and different values of the relaxation parameter, we can generate multiple cubo formulations, solve them using a cubo solver, using quantum annealing. Then we can calculate the probability of obtaining a feasible solution, the expected value of the objective function, and the standard deviation of the objective function, right? And so then we can train a machine learning model, the so-called solver surrogate, that can take another instance of our traveling salesman problem or vehicle routing problem or another optimization problem. And we can also take some other values of our relaxation parameter, but more or less the same range as was used in the training set. And then we can train our machine learning model. And once it's trained, it can give good estimates of the probabilities of obtaining feasible solutions and expected values and standard deviations of the objective functions. And then we can use another, but this time classical optimization algorithm to explore the space of different values of the relaxation parameter for a given instance of the graph and to propose a good value of this relaxation parameter. So, in my opinion, it's a brilliant idea, and it also gave quite good results that were published in this paper titled QROS, Cubo Relaxation Parameter Optimization via Learning Solver Surrogates. I think it's quite an interesting approach to enhance our quantum annealing or other solvers for applied to solving optimization problems. All right, that's all from my side. I have some extra slides just if there are some questions or would like to learn more. But let's see if there are some questions. As I think we still have about 15 minutes, right? I also
Yes,
provide links to my websites and email addresses. So if there are any questions later, feel free to reach me out.
perfect. Thank you so much, Dr. Gora, for the wonderful talk. We do have some questions. Several participants have raised their hands, as well as there are some questions in the chat. So if you can access the chat, then you will be able to see the questions from there.
Mm-hmm. Okay, so let me maybe just stop sharing for a
Or
while and
shall I read it to you?
I can let me just open the chat. Okay, let me open the
Perfect.
chat. Where is the? I can see that some people also raised their hands. Uh, so actually, honestly, I can. Okay, I can see the chat now. Yes. Um, can you please discuss the time taken by the quantum solver? Okay, I see the link to the paper from the wave. So there's a question from Hridayesh about the time taken by the quantum solver. Um, Hridayesh, could you please tell me what time you exactly have in mind to apply to which solver exactly? To the solvers for TSP, the traveling salesman problem, or another problems?
So yes, I am discussing on the TSP problems. Like if
Yes,
we are
yeah,
using the quantum solver, yeah, then what is the
yes,
time taken by?
yeah, yeah. Uh, so actually, it wasn't large. So these were just some fractions of seconds, right? So it was not large. I would say that the classical part, the classical part was more time demanding, more compute computationally demanding. But just the quantum annealer was run for only just fractions of seconds, so it was relatively quick. But it was quantum annealing, so we cannot guarantee, and we know that these solutions found by the solver were not optimal. And actually, in most of the experiments that I presented here, we used a simulator of a quantum annealing and not the actual quantum annealing because it turned out very quick that the quantum annealer that we had access to 5 years ago, or actually the experiments were carried out in 2019, so it was already 6 years ago. So the quantum annealer was not able to handle larger instances of our TSP and vehicle routing problem. And I see that you mentioned that QAOA is always better. It depends. So in terms of the compute time, perhaps yes, I agree. But we also tried to use QAOA and variation quantum algorithms for this, and it turns out that they also it was even not possible to solve larger instances with, let's say, more than a few customers and a few vehicles, because
Th-
the number of variables and the number of qubits that we need to use in this case is also large. Like, so it's, as far as I remember, it's more or less a square of the number of customers, and it's linear in terms of the number of vehicles. I think that this square can be reduced to n log n or something like that, but still, we can see that it's difficult to scale it with the contemporary quantum computers. Hmm.
Thanks for answering. Thanks a lot.
Okay. Yeah, there's also a question about the surrogate approach. It's really powerful but limited. I agree. So, when we apply machine learning techniques, it's only an approximation. Also, we try to replicate these experiments, and it turned out that it's not that easy. So we we started doing this research already more than 2 years ago, I think, and by now we haven't achieved sufficiently good results with this surrogate approach. Um, Perhaps there, so we, but and we even use the same code. The code for that paper was publicly available in a GitHub repository. But we just ran the code and trained our models on a different data set that was also randomly generated. So we had randomly generated instances and randomly selected values of the relaxation parameter. But the procedure of building the training set was different than the procedure that was described in the original paper. And it was enough to not achieve similarly good results and the results that were reported in the original paper. So it's difficult. The architecture of the machine learning model should somehow encode the input graph. It's also limited because when we train our machine learning model, we can train it uh, on limited graphs, like for example up to 100 customers. Okay, and we cannot easily insert or put as an input road networks with more customers. Okay, because
Yeah, I understand because the
yeah.
qubits will increase in a fraction of 2 raised to the power number of qubits.
So this is
Yeah.
one reason, but
So
even when you talk about the surrogate approach with machine learning, then when we have a neural network that takes let's say 50 variables as an input and we train it, then when we want to apply or take an input with let's say a few thousand of customers, then we would need to somehow squeeze this instance, somehow compress it to give it as an input to to the trained neural network. So this is challenging. There's another question: do we have data for solver surrogate method? So unfortunately there was no data set available in the repository of this original paper. So we had to generate the data set on our own, and we also generated it not using a quantum annealer but using a simulated annealer in this case, but applied to the same QUBO formulation. And as I said, it turned out that the results are not as good as it was reported in the original paper. So it's possible that the method of generating the data set is important as well, not only the architecture, because we used exactly the same code that was available in the open repository published by the authors of the paper, but our data set was generated in a different way, and we didn't observe similarly good results as the results that were reported in the original paper. So we didn't manage to reproduce the results from the original paper yet. Mhm.
Dr. Pavel, since you're answering this question itself, so do you think like there is a consistent reproducibility problem associated with these algorithms?
What do you mean by? Could you please repeat the last part?
Yeah, like you weren't able to reproduce the
Yes,
results from the
yes,
original paper. So is this a consistent
yes.
problem with the rest of the algorithms as well?
Uh, I'm not sure. So in general, based on my experience, very, very often it's difficult to replicate the results that are presented in papers published by other researchers. So it doesn't concern only quantum approaches or only this Kuros paper. I can tell you that just recently with my research group, we tried to replicate the results from several other new research papers. And it turned out that it's really difficult. So usually the problem is even with configuring the environment. So there are even some technical issues, or there could be also some other issues later. So it's not that easy. So it depends. So sometimes it's easier to do it. Sometimes it's difficult. Unfortunately, the problem is that very very often there are some hidden settings that were just assumed by the authors, and perhaps they were even not aware of the fact that these settings can uh, influence the results, right? And they just didn't report that, okay, so these were the settings that we used. for example. So it can happen as well. So in general, I think it's a general problem in science, especially computer science, recently, especially machine learning, that it's not that easy to replicate the results that are reported in the papers of other authors.
There are people who raise their hands too.
Yeah,
Right. Thank you.
I
Yeah,
think.
Shreyans, please go ahead with your question.
First of all, thank you. Thank you very much, sir, for such an interesting session. My question is based on more general, means more basic of quantum optimization. I always have this difficulty of mapping the problem to the polygates which are actually used in building the circuit. So, can you comment on that?
Hmm. Um, okay, so it is challenging because this is a really I think the main creative part of everything, of all these approaches, and it really requires some experience to do it properly, because as far as I know, there are already some algorithms on how to do it. So even when you ask some AI tools to generate, for example, to generate a Kubo formulation for a given problem, it can do it. There are already some handbooks explaining how to do it step by step. But when you apply some default techniques to do it, um, very often you will see that the number of qubits that you have at the end is so huge that you cannot really run it on contemporary quantum computers. So then there are always some optimization techniques, and then you can really go deep into the optimization problem, dive deep into the optimization problem that you have, analyze it, and try to look for some symmetries, and try to reduce the number of qubits. There are also some papers on reducing the number of qubits for the formulations that you have. So there are some procedures on how to do it, but it's also a matter of, let's say, experience and creativity as well.
Thank you very much, sir.
Yeah.
Yeah, Aradhya, please go ahead with your question.
Hello, Dr. Pavel. Thank you for such
Hello.
an insightful session. You mentioned that noise can help jump out of local minima. Since quantum computers are usually considered very noise sensitive and noise is typically avoided,
Mhm.
how does this possibility change the way we should think about fault tolerance in quantum optimization?
Okay, yeah. So maybe I will open the slide that I shared, and that concerns this question. Let me just do it, because yeah, this is interesting indeed. You know, can you see my screen now? Yeah, I
No.
hope you can. Oh, can you see it now?
Yep.
Okay, yeah. So this is exactly the point that you asked about. That VQA have been shown to be somehow resistant to noise, and some even claim that a pinch of noise might help with the optimization process, because it helps to escape local minima. And why it can be the case, why it's possible. Are you maybe familiar with the dropout technique from classical machine learning? So when you
Yes.
train neural, yes, it's one kind of regularization techniques. So it's
Mhm.
a regularization technique that you use when you train neural networks. So with a small probability, you can randomly remove some weight, some connections between neurons, or maybe even the whole neurons with all their connections, but usually rather the connections between neurons, right? And it's one of the regularization techniques, which means that it prevents overfitting. Because when we introduce this dropout during the training, then the other, or the neurons in the neural network learn that they have to be, let's say, more generalized, that they just cannot overfit to some very very specific tasks. So they learn to be generalized, so that when one weight of connections or a few weights of connections are lost, then they should still be able to reproduce good results, right? So that's why this is considered as one of the regularization techniques. And here the case is similar, because so even in classical machine learning, when we add some noise and randomly remove some weights, some connections between neurons, we can achieve better results. So it's not strange in this case, and I think that this case is kind of similar. That thanks to the noise, we ensure that our models are somehow, let's say, more robust. So if there are some small changes in the input, there could be just better generalization properties. So this is a reason why the noise might help during the training, and this is one of the reasons why these variation quantum algorithms are considered to be quite good for the NISQ devices, for these noisy intermediate scale quantum devices. But as I said, the question is if this, let's say, quantum noise that we can observe in nature, in the actual quantum hardware, can be simulated using classical computers as well. Because if so, then perhaps we can achieve similarly good results using our classical computers, right? So it's not a quantum advantage. So I think, as far as I know, this is an open question. So I think that it is possible that this particular quantum noise, and not some, uh, some and the noise generated using classical computers using pseudo-random generators, can really give better results. I'm not sure if that's the case, so I'm not an expert in this particular field, but it is possible that this quantum noise can give some advantages in terms of better generalization properties. I'm not sure if it answers your question, but I hope that I explain it better.
So, do you see that people will be exploring noise and how it like can be tuned, like that
Hmm.
path of opening up?
Yes, I think so, and as far as I know, it's already ongoing.
Okay.
Yeah, so
Yeah.
it's already happening. So there are already some research works on this. Hmm.
Thank you, sir.
Thank you.
Good evening, Paul.
Yeah, yeah,
Uh,
Neil, please go ahead.
yeah, good evening, Paul. Thanks for
Good
this
evening.
session. I had specific questions regarding the use case. This was regarding like some of the use cases in healthcare. So, are you aware of any translational work done there? Because I have tried some of my hands on like molecular biology, right, as well as nano NMR, ESR studies, right, where they elucidate the
Yeah.
underlying mechanism of spin effects in biology, as well as quantum coherence, MRI studies, absorption spectroscopy. If you
Hmm.
are aware of that or any literature, or your team, any of your extended team is
Hmm.
working specifically on use cases in healthcare?
Yes, I know that there have already been such use cases. So these QAOA and VQE algorithms that I also described at the beginning are quite suitable, especially VQE. They're quite suitable for, in general, quantum chemistry, and also simulating chemical reactions, let's say, so designing new materials, new drugs. So this is one thing. But you also said about MRI, and for this, I think I can recommend one interesting paper that was uh, um, published a few years ago about neuroimaging for Alzheimer disease, or predicting Alzheimer disease, and this was done using quantum annealing as well.
Correct.
I'm trying to look
I have,
for the paper on this.
I have sent you a request. Maybe then we can connect on LinkedIn.
Okay, let's do it on LinkedIn. Yes.
Sure. And the other thing
So
was another thing
sorry,
was,
sorry.
sorry, sorry to interrupt. The other thing was regarding brain organoids. So I saw certain, because I had participated in the Google research paper, right? They had an event on quantum healthcare. So there was another case on the, brain organoids using demonstration of quantum effects with individual neurons in the
Hmm.
Vivo system. So is it only like specifically like MRI which can be a case? Because these were certain use cases which were given. Because but I couldn't find anything on brain organoids for quantum effects.
Uh, Actually, I'm also not aware of that, but perhaps you can try to look at the paper that I shared here on the chat. So that was actually about this. It's called the title is Community Detection in Brain Connectomes with Hybrid Quantum Computing, and indeed they used quantum annealing there, and it was related to Alzheimer disease prediction. And there is something about connectivity, detecting relationships between brain connectivity pathology. So, oh no, they investigate relationship between brain connectivity pathology, for instance, as Alzheimer's disease. So perhaps this is something you can try to investigate or contact the authors, because honestly, it's not my domain of expertise, but I heard that this was quite a good paper. So you can, and it was
Got it.
published in Nature. It was published in Nature, which is already a good sign. So you can try to contact the authors, and I think that maybe they will be able to recommend more articles on this.
Got it, Paul. Yeah, sure. Appreciate your help. Maybe, yeah, if there is anything, I will get in touch with you on LinkedIn. Thanks.
Thank you. Thanks.
Okay, so I think we are already running over time, but do you perhaps can take another question?
Hi, great lecture. I had one question related to the VQAs. Um, you said in a previous doubt we talked about putting noise to escape local minima, but in normal neural networks you can like remove the dropout for the last layer, but in here the noise would even persist in the actual output, right? It'll accumulate.
Mm-hmm.
So like won't that affect, won't like experimenting with dropout actually lead to a bad output?
I'm not sure if I understand your question. Could you please repeat, maybe?
Like we were talking about we were talking about noise to escape the
Yes.
local minima
Yes.
in optimization.
Yeah.
Yeah.
Mm-hmm.
So won't the accumulation of noise actually affect the final result in the VQA for like long circuits?
I think that it depends on the scale of the noise, right? So if the noise is too large, then definitely. But this is the same when you apply this dropout technique in classical machine learning. So this is usually the probability of dropping some connections between neurons is a hyperparameter that you have to tune, and usually you have to set really really small values of this probability, like less than 1%, like 0.1, 0.01 probability. So with this kind of noise, then it's not that big issue, uh, and indeed, it can help escape local optima. It can ensure better generalization properties, perhaps. So usually it helps a bit in case of training classical neural networks. So in this case, I believe that if this noise is not huge, then it shouldn't significantly affect the results. But if the noise is at the level like 1%, 10%, then definitely I will not expect good results. So perhaps it would be difficult to converge to good
Okay, so again
solutions.
it's very
Mhm.
experimental.
Yeah, it's very experimental indeed.
Okay, okay. Thank you.
Thank you.
Okay, so I don't see any more questions. So once again, on behalf of the Qiskit Fall Fest IIT Jodhpur, I would like to express my sincere gratitude towards Dr. Paweł Gora for the amazing talk and for also answering all our questions and queries.
Thank you. Thanks once again. Good luck, everyone, in your quantum journey.
Yes. Thank
Bye
you, sir.
bye.
Bye bye.